Hey guys, Mr. Wemp here. I wanted to talk about the board game counter and the digital portion that you'll be working with. So basically, prior to that, you have created an analog portion, and that analog portion is giving you a clock pulse. And so basically, it's giving you this into what you created with a sequential logic portion. So we had sequential logic, and in that sequential logic, the sequential logic converted that pulse into a series of binaries. So basically, it gave us a number of 1 through 6 in binary. And so that binary came out as 1 through 6, and then it has to go into another set of logic, which is our combinational logic. What the combinational logic does is converts this binary 1 through 6 into specific outputs. So in our purpose, the output, which would be the dice. Okay, so we're going to take a look at that in a presentation. So basically, it goes to here, and then it goes to here, and then it goes to digital dice like that. So it could roll any one of those numbers. Okay, so that's what we're going to take a look at now. Let's take a look at, basically, this is our output here. And so when we're dealing with this particular game, when we press the button, the analog portion will create the roll. That'll create the signal. And when that signal runs out, whatever it happens to land on is what will be displayed down here. And so what you're going to see, or what you won't see actually, is this thing counting 1, 2, 3, 4, 5, and 6. But it'll be cycling through so fast that it'll look like all these lights are just on. So essentially it makes you think that it's thinking about it, but really it's just counting very, very quickly. Here's what it looks like going in. This is what I just kind of drew. You have your clock going in. The sequential logic is dividing by 2 each time. And so basically here's your original clock pulse. You have 1, 0, 1, 0, 1, 0. The second one is going to be 0, 1, 1, 0, 0, 1. So you have basically 2 zeros, 2 ones, 2 zeros, 2 ones. And then the third one, once it divides that again, now you have 3 pieces. So you have 3 different options here, and this is how you would count from 1 to 6. All right? And then the combinational logic, this would be AOI. This would be right here, this would be flip-flop. Okay, so we have flip-flops and AOI. The AOI is going to take this conversion here and say, okay, well, if I have a 1, 1, 0, then my output needs to go to, I don't know, L1, L4, and L7. So those 3 lights will need to turn on whenever I see this number pop up. And so that's what's happening. So it's converting each time. Okay, so in the sequential logic section, we basically have our 3 flip-flops, the clock coming in from analog, and we have these 3 flip-flops, and then they do their count. And there's a little bit down here, which is actually some combinational logic. This is what sets and resets our clock, or excuse me, our counter. So when this counter reaches the max, when we have 1, 1, 1, you can't count any higher than that. So instead of just being stuck there, we want it to start over and go to 0, 0, 0, right? We want it to switch over to that. We want it to change. So the only way that that has to happen, or that can happen, is that when this is a 1, 1, 1, so we have a 1, 1, 1, we come down here, we have 1, 1, which goes through an AND gate, so 1 and 1 is 1. And then this 1 comes down, and we have 1 and 1, which is an AND gate, is 1. All right, so mom and dad said we could go, and we can go. Now, what has to happen in order for these guys to reset back to 0 is that your clears have to show a 0, because remember, the 1 is keeping them closed. Well, if this is a 1 coming through, it's already a 1. That's not going to let it keep counting. We want it to switch all the way over. So then that 1 has to go through this inverter, and it pops out as a 0. So then that 0 goes there, and goes there. And now when these clears are 0, all of a sudden it clears out your data, and the second that that clears out, guess what happens? All your outputs up here are 0, 0, 0. Well, now 0, 0 is not 0, or excuse me, not 1, so you end up with 0, and this 0 drops down, you have 0, 0 again, so 0, 0. That pops out as a 0, so cross out these 1s because we're on a new one. Well, 0 inverted to 1 is here, and it goes here, and these all pop back to 1, and that allows it to count. So basically it's resetting itself, okay? And so it's counting up 1, 2, 3, 4, 5, 6, and then it cycles through and does another one. All right, so here's what it would look like on the count of 1. Here's our clock on the rising edge. Okay, we have a rising edge there. So we have logic 0 because we're on down on logic. So the clock comes in on 0. That means that D pops in here and Q comes out, and we have our pulse of 1. So 1, 0, 0, right? And then it sends the Q naught into here, so our clock is 0, which gives us no clock. All right. So if we go to the next count of 2, we have it coming in. We have this guy is a naught because now we're dividing by 2, so now this guy is controlling it, and it basically sends a signal, a logic 1. So Q is, well, Q should follow D, but we've got the clock comes in, so my data says it's a 1, so Q is a 1, pops up there. Q naught comes in here, and the clock is 0, so Q is going to be 0. So we have 0, 1, 0, which is 2. We get to 3, and we have 1, 1, 0, and you can kind of see it's doing the same thing each time. And our things are switching. Count of 4, 1, 0, 0. And then 5, 1, 0, 1. And 6, 1, 1, 0. And there is no 7th count, so we won't count to 7. You could. If you had 1, 1, 1, that would be 7. But if you notice here, we have a 1 and a 1 that comes in. We have the 0, so we don't want it to reset on 6. We want it to get through 6. So on 7, 1, 1, 1, that's when we'll end up with the situation where we have a 1, and a 1. Okay, so it resets on 7. It uses up 7 as the reset. So it does have to count to 7. It's only going to display 6. All right, so basically here it is again. This is your diagram. You push the button in the analog. That produces a dampened square wave, so your wave comes in. The sequential logic is going to turn that into pulses. So on every pulse of the clock, the sequential logic section creates a binary count from 1 to 6. When it gets to on count 7, that's the reset, so it goes back to 0 and counts through again. Actually, it resets to 1. And then that output comes into combinational logic, which then turns it into some kind of a code. So what does that look like? Combinational section is the pretty easy one. It looks like this. So if I have, let's see, 0, 0, 1, I have this guy coming in, and if you look at it, you'll be able to follow along and see that, well, this would light up, should light up this middle one, which is only this guy, which is that one. So 1 comes in here. All these others would end up being 0, and we've got it wired to the center probe. Okay. Here's a truth table that we would set up. We have our inputs, A, B, and C. This could be X, Y, and Z, 1, 2, 3, doesn't really matter. But those are our inputs. And in this particular section, our function has 7 different functions. Okay, so in a situation where 0, 0, 0, none of them light up. 0, 0, 1, the only light that we want to light up would be 4, or light 4. We have, looks like, I think it's 1, 2, 3, 4, and then 5, 6, 7. So we have 7 different lights. And then you just go through it. So this function has, like I said, 7 different properties. And so in a situation like this, where it's 6, I want these 3 to light up and these 3 to light up all at the same time. Okay. Again, that would be what this is right here. So if I have, let's get rid of this and we'll call it 1, 1, 0. So this is 0, this is 1, this is 1. it comes in here. I have a 1 in the OR. Right here I have a 1 and a 0. So mom and dad, they said no, so I have a 0. And this one is a 1 and a 1. And this guy is a 1 and a 1. So basically I have mom or dad, so that one's going to light up. Remember, this should be 6. This little output here, mom and dad said yes, so that's going to light up. This turns into a 1, so anything that's a 1 is going to light up. So there's 1 there, there's 1 there. And then on this guy right here, mom and dad agreed, so we know that's going to be a 1. So what lights up? Well, that's attached there, and that one's attached there. Oh, and this guy here, the wire is attached there, so that one's lit up there. So with this circuit, we get a 6, and you can see it rolling a 6 right there. Okay, so if we look at this guy, this is how the logic flows through. We just kind of walk through that. So on each count, the logic changes, and you can feel free to pause the video and kind of follow the logic here. But there's a count of 4, so you see 4 lights, 5 lights, 6 lights. Now, the only reason this looks like a dice is because we have the lights lined up where they belong. I could line these up in a row and have just some random number of lights lighting up, and it wouldn't look at all like what you would think it should. Okay, so if we want to convert those from probes to LEDs, we have the same setup. This time we have, this is the LED symbol, and if you have an LED, you have to have a resistor, and then basically this is the same setup as what will be on the physical board itself, but when you simulate it, you can use the LEDs in this form. You can also use the probes. I think the probes are a little bit easier to see. And finally, when you combine it all together, you have your sequential logic. So here's your count. So these are your flip-flops here. Flip-flops. Here is your reset. Here's your AOI logic. And then that outputs to your 7 different functions. And then the analog we did earlier. Okay, so basically that is how the game board counter will work. When you're working with the flip-flops, just keep in mind that it's counting. So this would count 0 and 1. This will count 0 and 1. This will count 0 and 1. But because you have 3 flip-flops, you have 3 pieces of data. So you have the possibility of counting up to 7 with these 3 pieces. Okay, so that's the game board counter, the digital portion. You would then come in and plug your analog in for your clock, and you'd be good to go. All right, we'll see you next time. Bye.